There's a simple, seemingly ironclad rule in the universe, right? Big planets need big stars. You just can't build a colossal, gas giant world without a massive, sprawling construction yard of gas and dust. For decades, this wasn't just a theory. It was a cornerstone of astronomy, etched into every textbook and lecture hall. It made perfect sense, too. The bigger the star, the more material it collects when it forms, and the more leftover cosmic building blocks are available for its planets. But what if that fundamental rule, that cosmic law, has just been absolutely shattered? Astronomers have just stumbled upon something that, by all accounts, shouldn't even exist. A gas giant planet so unbelievably massive, and its host star so incredibly tiny that it's forcing them to completely rewrite everything we thought we knew about how solar systems are born. This isn't just a minor tweak to a model. This is a full-blown cosmic curveball. This, my friends, is the story of an impossible planet, a celestial rebel that's defying the odds and making us question everything we thought we understood about our universe. Get ready, because the cosmos just got a whole lot weirder. For as long as we've been peering through telescopes and hunting for exoplanets, we've pretty much assumed that a star's size sets the entire budget for its planetary system. Think of it like this. A star like our Sun, a respectable yellow dwarf, comes with a rich, bustling protoplanetary disk. This disk is a swirling, colossal cloud, absolutely heavy with hydrogen and helium, the perfect ingredients for growing behemoths like Jupiter and Saturn. It's got all the raw material you could ever dream of, a cosmic buffet ready for planet formation. But then you start shrinking the star, and guess what? You shrink the disk right along with it. It's like downsizing your construction site. Drop below about half a solar mass into the realm of those ubiquitous, faint red dwarfs, and suddenly, the disk is supposed to be far too light, too wispy, to ever make anything bigger than a rocky super-Earth. We're talking about stars that are barely bigger than Jupiter, with disks that, theoretically, wouldn't have enough material to even form a substantial pebble, let alone a gas giant. The leading theory for how gas giants form, called core accretion, is pretty straightforward. It says you first need to build a solid, rocky core, one that's at least 10 times the mass of Earth. Only then, once that massive core has formed, can it start to vacuum up a thick, dense atmosphere of hydrogen and helium from the surrounding disk. Without enough raw material, that initial core never forms. And without the core, well, there's no gas giant. It's a pretty strict recipe. Textbooks were crystal clear on this. Red dwarfs get small, rocky worlds. Maybe a few of them, but definitely nothing enormous. End of story. Or so we thought. Then, out of the cosmic blue, along came TOI 6894. NASA's TESS satellite, a workhorse of exoplanet hunting, was doing its usual thing, just performing its routine, meticulous sweep across the night sky. It was monitoring over 91,000 low-mass stars, patiently looking for that telltale dip in brightness that signals a transiting planet passing in front of its star. It's like a tiny eclipse, a momentary wink. And then it happened. One pixel, just one tiny, insignificant pixel in TESS's vast field of view, flickered. A 1.4% drop in brightness, repeating every 3.3 days. That's it, just a pixel, a subtle change. But those sophisticated algorithms, the ones designed to catch these cosmic whispers, flagged it. Then, human eyes, trained and meticulous, confirmed it. And from there, a worldwide network of astronomers and telescopes swung into action. Within months, the scientific community mobilized. The mighty Very Large Telescope in Chile, a marvel of engineering, turned its gaze. TRAPPIST, a dedicated planet-hunting observatory in Belgium, joined the effort. And the Speculus arrays, located in the pristine high-altitude deserts of the Atacama in Chile, all measured the exact same periodic wobble. They weren't just seeing a dip in light anymore. They were seeing something truly massive, something hefty, yanking on that tiny star. It was like watching a chihuahua trying to walk a Great Dane. The tail was wagging the dog, or in this case, the planet was tugging on the star. The numbers that came back were frankly jaw-dropping. The star itself? Only about 20% the mass of our sun. That's tiny, but its companion? A Saturn-sized world packing an astonishing 53 Earth masses of material. Let that sink in for a moment. A gas giant, nearly twice the diameter of Earth, hugging its star tighter than Mercury hugs ours, completing an orbit in a mere 79 hours. That's fast. Nothing that small, nothing that dim should host anything that big. It just doesn't compute with our current understanding. Yet there it is, blazing a 300-degree trail across the star's face, a cosmic enigma challenging everything we thought we knew. It's like finding a blue whale in a goldfish bowl. Cue the cosmic double-take. This isn't just an anomaly. It's a full-blown scientific puzzle, a head-scratcher of epic proportions. How, in the name of all that is astronomical, do you build a planet half the mass of Saturn from a disk that, on paper, should barely contain more than a scattering of rock and ice? It's like trying to bake a 5-tier wedding cake with only a single cup of flour. The star's meager light output doesn't just imply a meager disk. Our best models explicitly predict a few Earth masses of material at most in the protoplanetary disk around such a small star. Even if every single speck of solid material in that tiny disk coalesced perfectly, efficiently, miraculously, you'd still fall drastically short, by an entire order of magnitude of what you'd need to form TOI 6894b. It's just not enough stuff. And migration? While it's true that giant planets can indeed spiral inward from farther out in a system, that doesn't actually solve the fundamental problem of formation. They still had to form somewhere with enough raw material. TOI 6894b isn't just migrating. It's parked right where the raw material should have been thinnest in the first place, impossibly close to its diminutive star. So, we're left with a stark choice. Either our long-held disk mass estimates for red dwarfs are catastrophically wrong, wildly underestimating the cosmic construction materials available, or giant worlds have a second, entirely different, and much faster birth channel that we've simply never witnessed before. It's like discovering a new species of bird that can fly without wings. This planet is forcing us to confront a profound gap in our understanding. Astronomers, being the persistent truth seekers they are now chasing down 3 possible escape hatches, 3 ways this impossible planet might have come into being. Each one challenges our current thinking in a different, intriguing way. Maybe, just maybe, the disk around TOI 6894 was secretly supersized. We know that red dwarfs can be surprisingly metal-rich. If TOI 6894 happened to form in a particularly dense, dust-laced region of its stellar nursery, its protoplanetary disk might have been far more massive than our typical models predict. It could have exceeded the normal budget, giving the core accretion process, that slow, steady buildup of a solid core, a fighting chance, even around a tiny star. It's like finding a hidden stash of building materials at a small construction site. This would mean our assumptions about the average disk mass for red dwarfs might need a serious reevaluation. This one's a bit more dramatic: gravitational instability. Imagine a massive, dense protoplanetary disk, not necessarily rich in heavy elements, but just incredibly cold and turbulent. In such conditions, instead of slowly building up a core, chunks of gas and dust can collapse directly under their own gravity, like a sudden implosion, forming a planet almost instantaneously. This mechanism completely skips the slow, meticulous core building phase. It's a fast track to planet formation. The catch, though, is that you need a truly massive and incredibly cold disk for this to happen. Conditions like that are generally considered quite rare, especially around tiny, low-mass stars like TOI 6894, which often don't have the gravitational heft to pull in such a huge initial disk. It's a tantalizing possibility, but it requires some pretty extreme circumstances. And then there's the idea of post-formation chaos. Perhaps TOI 6894b wasn't born so close to its star at all. Maybe, just maybe, it was born much, much farther out in the system, in a region where material was plentiful, where forming a gas giant was entirely unremarkable. But then, through a series of gravitational slingshots, close encounters with other nascent planets, or interactions with the remnants of the protoplanetary disk, it embarked on a wild roller coaster ride inward. It could have scattered smaller siblings, kicked them out of the system entirely, and then, after a chaotic cosmic journey, parked itself in the current, incredibly tight orbit we observe today. It's like a game of planetary billiards, where one massive ball clears the table and settles into a pocket. Each of these scenarios leaves a different, distinct chemical fingerprint in the atmosphere of the planet. And this, my friends, is where the hunt turns truly exciting. Because TOI 6894b's transits are so deep, over 1% of the star's light is blocked. Its upper atmosphere is beautifully backlit when it passes in front of its star. This makes it an absolutely prime target for next-generation observatories. Telescopes like the James Webb Space Telescope, with its unparalleled infrared vision, can sniff out these atmospheric clues. It can detect the signatures of carbon, oxygen, and other heavy elements, telling us whether this world built itself slowly, grain by painstaking grain, through core accretion, or if it collapsed in a single, dramatic swoop of gravitational instability, or perhaps even bears the scars of a violent migratory past. The atmosphere holds the key to its impossible birth. Why does this one impossible planet matter so much? Well, let's talk numbers. Every small star we look at, every red dwarf, multiplies the potential for planetary systems. These stars are, quite simply, the most common type in the universe. Roughly 3/4 of the Milky Way's staggering 400 billion stars are red dwarfs. Think about that for a second. If even a tiny fraction of them can churn out gas giants like TOI 6894b, the cosmic census for giant planets just exploded. Our previous estimates for the sheer number of gas giants out there could be wildly, fundamentally off. And here's where it gets even more intriguing for the search for life. Rocky moons orbiting these newly discovered gas giants could potentially host liquid water. Imagine a Saturn-like planet, with its majestic rings, adorned with dozens of Earth-sized moons, all protected from harsh stellar flares by the gas giant's thick hydrogen blankets and powerful magnetic field. The red dwarf itself, while dim, is incredibly long-lived, providing billions, even trillions of years for life to potentially evolve. TOI 6894b proves that this blueprint, this seemingly impossible scenario, actually exists. And that means more surprises are undoubtedly lurking out there, waiting to be found. This discovery isn't just a scientific curiosity, it's a game changer for how we prioritize our searches. Upcoming surveys, missions like Plato, the Roman Space Telescope, and a next-generation TESS extended mission, are already retraining their search algorithms. They're specifically looking for these oversized shadows around undersized stars. Each new detection of a planet like TOI 6894b will tighten the statistical thumbscrews on our formation theories, forcing theorists to rewrite the rulebook in real time. It's a dynamic, exciting field where every new data point has the potential to overturn decades of established wisdom. We're on the cusp of a revolution in planet formation theory, all thanks to one little star and its impossibly big planet. So, where does this leave us? What does TOI 6894b mean for our understanding of the cosmos? Well, that old mantra, that comfortable assumption of small star, small planets, is officially dead. The universe has demonstrated, once again, with breathtaking elegance and a dash of cosmic defiance, that it is far more inventive, far more imaginative than our textbooks, our models, or even our wildest science fiction. TOI 6894b isn't just an oddball, a statistical fluke that we can ignore. No, it's a neon sign, blazing brightly across the galaxy, pointing directly to physics, to processes, to formation mechanisms that we've simply overlooked. Whether the ultimate solution involves fatter, more massive disks than we ever imagined, or faster, more dramatic collapses of gas, or even a chaotic game of planetary billiards, the implication is the same, and it's profound. Giant worlds can absolutely thrive in miniature ecosystems. And if that's true, it fundamentally rewrites the odds on where life, in all its myriad forms, might emerge. Imagine, for a moment, a Saturn-like planet, with its majestic rings and swirling storms, adorned not just with a few moons, but perhaps dozens of Earth-sized moons, each a potential haven. And all of this orbiting a star so dim that its noon feels like a perpetual twilight, a soft, reddish glow. Science fiction? Not anymore. This is the new reality that TOI 6894b is nudging us towards. It's a universe richer, stranger, and more full of possibility than we ever dared to dream. Astronomers set out to confirm a rule, a long-standing principle, and instead, they utterly broke it. TOI 6894b, the giant planet circling a star barely bigger than a cosmic spark, has quite literally yanked the rug from under planet formation theory. It's not just challenging, it's inviting us, compelling us, to fundamentally rethink what's possible in the darkest, most common corners of the galaxy. It's a humbling reminder that our scientific models are always works in progress, always subject to the universe's boundless ingenuity. The next time you glance up at the night sky and your eyes fall upon one of those faint, reddish stars, remember this. It might be hosting a world that, by all accounts, has no business existing, yet stubbornly, gloriously does. Keep looking up, keep questioning the impossible, and absolutely stay tuned, because the universe, in its infinite wisdom, is already plotting its next rule-shattering surprise. If you're enjoying this cosmic whodunit, this journey into the impossible, do yourself a favor. Tap that subscribe button and ring the bell so you don't miss when the next impossible planet shows up. Trust me, the universe always has more surprises in store.